All right, today we're going to pull back the curtain on a piece of tech you use literally every single second you're online, but you've probably never even heard of it. I'm talking about the adaptive filter. It's this silent, invisible engine that makes our kind of chaotic digital world feel smooth and clear. So let's dive right in.
Yeah, seriously. Ever wonder about this? You're on a video call, right? Your voice comes out of their speakers, their microphone picks it up, and it gets sent straight back to you. Without some kind of serious tech magic, you'd just be hearing this awful, delayed echo of your own voice the entire time. So why don't you? Well, you guessed it. The answer is an adaptive filter. So here's the core challenge. In the real world, signals are just messy. They aren't clean and predictable like they are in a lab. So a standard, fixed filter, it's pretty much useless if it doesn't know the exact characteristics of the noise it's supposed to be canceling. And the thing is, in telecommunications, those characteristics are changing. We're talking millisecond by millisecond.
So how do you even begin to solve a problem that's constantly changing like that? Well, you create a solution that can change right along with it. And that, right there, is the whole idea behind adaptive filtering.
Okay, so here's the core concept. An adaptive filter isn't built with, one fixed set of rules. Instead, it has these things called adjustable coefficients, but you can really just think of them as digital tuning knobs. The filter also has a built-in learning algorithm, and its whole job is to constantly retune those knobs, adjusting itself to perfectly cancel out whatever noise or distortion is happening in that exact moment.
Honestly, this is my favorite way to picture it. Imagine a musician, maybe a guitarist in a band, who hears a note going just a little bit flat. And in a split second, without missing a single beat, they reach over and retune the string. That's exactly what an adaptive filter is doing, but it's doing it hundreds, maybe thousands of times every single second inside your devices. It's performing and retuning at the exact same time.
And what's really cool about this process is how elegant it is, at least in theory. It's this constant loop. First, it processes the incoming signal. Then it compares its own output to what a perfectly clean, desired signal should look like. Step 3, it calculates the difference between those two. That's what we call the error. And finally, step 4, it adjusts its internal knobs to make that error smaller. The filter's entire goal, its whole reason for being, is to get that error as close to zero as possible. That's what engineers call minimizing the mean square error.
But of course, there's more than one way to teach a filter how to learn, right? Engineers mostly rely on two major algorithms to make this whole adaptation process happen. And, they each come with their own set of pros and cons.
And this brings us to a classic engineering trade-off. On one side, you've got the least mean square algorithm, or LMS for short. This one's the reliable workhorse. It's simple, it's efficient, and it doesn't need a ton of processing power. Then, on the other side, you have the recursive least squares, or RLS, algorithm. Now that one is the high-performance race car. It gets to the right answer way faster, but it burns through a whole lot more computational fuel to do it.
And that right there explains why the simpler LMS algorithm is just so dominant. Think about it. When you're building millions, even billions, of phones, modems, or headphones, that low computational cost is a huge advantage. It means you don't need a supercomputer to cancel a simple echo. You can do it with a tiny, super efficient chip. And that's exactly what has allowed this technology to become so widespread.
Okay, so now that we have an idea of how they work, let's talk about where you actually find them. And the answer is, well, pretty much everywhere digital communication is happening.
So yeah, we've already covered echo cancellation in calls, which is a big one. But look at the range here. You've got channel equalization. That's a fancy term for cleaning up messy data signals, which is crucial for clear Wi-Fi and modem data. Then there's suppressing interference from things like noisy power lines. They're even used in really advanced stuff like predictive speech coding and in adaptive sensor arrays to get a much clearer signal from a bunch of different sources. It's a lot.
But let's just pause on that channel equalization point for a second, because this one is huge. The only reason we were able to get high-speed DSL internet running over those ancient copper phone lines, the ones that were never ever designed for data, is because adaptive filters could learn the unique quirks and distortions of every single phone line and just cancel it all out in real time. It's kind of amazing. And this is really the key idea. They don't just fix a problem one time and call it a day. The crucial part is that they track channel variations. So if the noise on the line suddenly changes, maybe because your neighbor turns on a blender, the filter adapts instantly. It's this constant, dynamic process of compensation.
So what's the big takeaway here? It's that pretty much every piece of clear, fast, reliable digital communication that we all just take for granted, well, it's all standing on the shoulders of this one technology. It really is the unsung hero that takes our messy, unpredictable analog world and forces it to play nice for our clean, structured digital lives. And that really leaves us with a fascinating question to chew on. We've successfully applied this powerful principle of adaptation to signals, but the core concept is so much bigger than that, isn't it? In a world where everything from our climate to our economy seems to be in constant flux, you have to wonder, what's the next big problem we can solve by making our technology truly adaptive?